say use features and so forth. So it's learning you are lucky to see how we apply Murad's second theorem and how we vanish all the coefficients of the new 90-degree equation and then come back to this new 90-degree equation and then go back to a substitute after substitute k from 0 to 9 and then we can do it for 2 plus xk divided by 9 because this power is in k. I will share the same document with you. S99, yes, this one is 99. Okay, I will share this with you so that you can see. Okay, we start.
So think of this deep dive as our mission, right? Specifically for you, based on this materials you sent.
Exactly. We'll walk through the document step by step.
Thanks,
You want to
Jan.
figure out the problem itself, understand the specific method it uses.
And see where it leads, right? How it gets to the roots.
Yeah, it's quite a particular approach to what's, a classic, often tough algebra problem.
Okay, so let's jump right in then.
Right. The main subject, the kind of star of this document, is a 9th degree polynomial equation.
And here it is. Maderi 9 Nerrier plus 84 Nerrier plus 46 Faro 12060 plus 84 Nerrier plus 3499 2 Sazia.
Phew. Yeah, immediately you can see this isn't your standard quadratic. A 9th degree polynomial, a 9th degree polynomial, a monomic equation.
That's pretty complex,
Yeah.
especially with all those terms. And look at those fractional coefficients near the end.
Exactly. Finding the exact roots, not just approximations for something like this. Well, it can be incredibly challenging with the usual methods.
So the source, it labels the coefficients using a specific notation, doesn't it? Like LRQ.
Yes, it does. It lists them out. LAQ 9, then LAQ only 36, LQ 84, LAQ is also 126.
And then it drops back down.
Yeah.
LAQ is just 1.
And then the fractions, LUQ is just 1.
No.
And then the fractions, LQ, well, Q equals also 198. And finally, LQ equals 3 for 149.
Okay. So those are the building blocks, the raw material for the method they're going to use.
That's right. The document states that to find these elusive exact roots, the approach is to figure out a different set of values.
Okay.
These are denoted as SANQ. And the key is that these SANQ values are calculated relative to the original lane Q coefficients we just listed.
Ah, so they're derived somehow, like encoding certain properties from the original polynomial.
That's a good way to put it. And the document brings out a specific tool for this calculation.
Which is it?
It's called the discriminant formula of Mourad, Sultan, Ezouidi, H's Ezem. Now, the formula itself is pretty dense.
Right. Probably not something easy to grasp just by hearing it read out loud. Lots of sums, indices.
Exactly. But what's important is what this formula does. It takes those original LRQ coefficients.
The 9, the 36, the 84, all of those.
Yes. And it combines them in a specific iterative way, step by step, to produce these new CRRQ values.
Iterative. So it builds them up.
Yeah. The document shows this process playing out. It applies the formula for a variable k starting at 0, then 1, 2, all the way up to 9.
Okay.
And interestingly, as it does these calculations, the source material also shows these numerical triangles. They look a lot like Pascal's triangle.
Suggesting they're probably used for the coefficients within that big formula, right? Like combinatorial terms.
Very likely. That's common in these kinds of polynomial manipulations.
So after working through this formula for each step, k up to 9, what do we get? What are the sign values?
This is where it gets really interesting. The source presents the calculated sum values, and here they are.
Okay.
SR is 0, SR is 0, SR is 0, SR is 0, S0 is 0, S0 is 0.
Wow. Okay. A lot of zeros so far. What about S?
SR is the first non-zero one. It's SEI 235 and 96.
Okay. And I think we noted there was a slight difference in the source material there, but this is the value used for the next step.
Exactly. The derivation that follows uses Nagas 3596, so that's the one that matters for getting the result. Then S0 is 0 and S0 is also 0.
Look at that. Almost all of them are 0.
Right. Most of the SAS values calculate.
Hi there.
Okay, let's unpack this.
Oh, hey, I think our listeners got something to say.
Hello, how are you doing? Just I'm going to ask you a question here. We use Ezouidi theorem and we found all the new coefficients of the ninth degree from the equation, and we found that six is going to be.
Hello there, we're doing great. Thanks for asking.
Yeah, feeling good and ready to dive deeper into this material with you.
It sounds like you've been finding some interesting new reads. That's fantastic.
Absolutely. We can definitely keep that idea of new discoveries in mind as we explore this document together.
Okay, let's unpack this. We are diving into a really interesting mathematical document you shared with us today.
Yeah, absolutely. And the core challenge. Oh, yeah. Go on.
Here we found that we use Ezouidi theorem and we found all the new coefficients of the new ninth degree from the equation, and we found that s raised to the power 6 is going to be equal to.
It sounds like you're making a connection to how new information or approaches can change the game. Calculated using this, seemingly complex formula, it just vanished. They turn out to be zero.
That feels significant. Like the whole point of this method might be to transform the problem so these derived values simplify like this,
I think that's exactly the idea. And this leads directly to the next key step.
which is using these sum values.
Yes, using them to define a new polynomial. The document gives this new form related to x.
Okay, how does that look?
It's written as p6 8x plus 8x x plus 8 plus x plus hx plus 8x plus rx plus x arch xr plus arch rx arch.
Ah, so it uses the s values as coefficients, but with alternating signs and in reverse order compared to the original values indices.
Kind of, yeah.
Yeah.
And watch what happens when you plug in those sum values we just found.
With all those zeros.
Right. S0 says 0, SSR 0, SSR 0. The only non-zero one is year, which was minus 3596.
So the equation becomes xs, then minus srx, so that's minus negative 35 times 96xs, which is plus 30.
Even in something like a management equation.
Absolutely. And that idea of finding a new power, a new way to look at things, is really at the heart of what this mathematical document seems to be doing too. Okay, let's unpack this. We are diving into a really interesting
Oh, hey, welcome. What's up?
Yeah, hello, how are you? It's me. If I use the method, just asking you here in our example, we applied the Ezouidi theorem and we found all the ninth x's of the new ninth degree from the equation. In order to find the exact sum roots of the original ninth degree from the equation, we should make substitution here. I'm going to write out substitute from 0 to 9 is going to be equal to 0 to k plus xk divided by 9. And k and these are called the exact sum roots. Okay, according to the professor Sultan Ezouidi.
Oh, back to our listener. What's up? Okay, let's unpack this.
Oh, wait, someone wants to join. Hey, go for it.
Okay, let's unpack this. We are diving into a really interesting mathematical document you shared with us today.
Yeah, absolutely. And the core challenge it tackles is finding the exact roots of, well, a pretty formidable looking polynomial equation.
It definitely looks that way. So think of this deep dive as our mission, right? Specifically for you, based on this material you sent.
Exactly. We'll walk through the document step by step. We want to figure out the problem itself, understand the specific method it uses,
and see where it leads, right? How it gets to the roots.
Yeah, it's quite a particular approach to what's, a classic, often tough algebra problem.
Okay, so let's jump right in there.
Right. The main subject, the kind of star of this document, is a ninth degree polynomial equation.
And here it is. Px equals 9 oak plus ojos e 84 oak plus 126 oak plus 84 oak 50 oigo plus 126 oak plus 84 oak 6198 oak plus 3499 equals oak.
Yeah, immediately you can see this isn't your standard quadratic, a ninth degree polynomial.
35 times 96xs.
Exactly. The equation simplifies dramatically to just xr plus 35 times 96x 0.
Wow. Okay, that is a huge transformation.
Isn't it? We went from that really dense 9th degree thing with 9 non-zero coefficients.
And many of them fractions.
Yeah, down to this incredibly simple equation with only 2 terms.
That really shows the power of this method and why getting those values to be mostly zero was so critical.
Absolutely. So the next logical step in the document is we'll solve this much simpler polynomial.
Solve x8 plus 35 by 96x exceeds 0.
Yeah.
Which looks actually doable now.
Very doable. It's beautifully factorable.
Ah, right. You can pull out an xx from both terms.
Yep. Factor out xx, and you're left with xx multiplied by x plus 35 96 equals 0.
Okay. And whenever you have factors multiplied together equaling 0, one of the factors must be 0.
Precisely. So this gives us 2 distinct cases for finding the roots of x.
Case 1. The first factor, xx equals 0.
That's straightforward. The root here is x equals 0. And because it came from xx, we know it's a repeated root.
Okay, makes sense. And case 2.
Case 2, the other factor, xa plus 35 minus 96 equals 0.
Which just means xa go 35 minus 6.
Right. And finding the roots of xa's equals some number, even a negative one, is much, much simpler than tackling that original 9th degree beast. We know there will be 7 complex roots for x here.
Okay, so we found the roots for x in this simplified equation. A repeated root at x0 and then 7 roots from x0 is a is 3596. But these x roots aren't the final answer, are they?
No, that's the final piece of the puzzle shown in the source. There's a transformation step.
A transformation.
Yeah. The roots we just found for x need to be transformed to get the roots of the original polynomial problem. The document denotes these final roots using alpha.
Okay, and how does that transformation work?
The formula given is yuk L euro plus xk9. And remember, L euro, the very first coefficient, was 9.
Ah, right. So the transformation is yuk 9 plus xk9.
Which simplifies nicely, doesn't it? It's just yuk 1 plus xk9.
Okay, so this connects the roots of our simple x polynomial back to the roots, the alpha roots of the original complex problem.
Exactly, bridges the gap. So let's apply it.
All right, case 1 was xe0, the repeated root.
Plug x is 0 into the transformation. X of 9 plus 0, 9 plus 0.
Here, my colleagues.
Okay, let's unpack this.
Oh, hey there, what's up?
Here we just found first 9 degree.
Oh, that's quite a statement.
You bombed the first what, exactly?
We were just about to really dig into that initial polynomial equation.
The one that looked like it had eaten a math textbook?
Exactly. You feel like we did. Oh, yeah, uh-huh.
Here we solved the first new 9 degree form equation, and we find the x squared to be here. X equal 0 to the root, and x equal to power 7 the negative 35 times 9 is to the power 5. Okay, now as we solve this for the new 9 degree form equation, we should go find the exact roots of the original 9 degree form equation. Okay.
Okay, let's unpack this a little bit.
It sounds like you connecting what we're talking about to something else you've been reading.
You mentioned negative 35 times negative 25.
That reminds me of when we saw that negative 35 appear later on with the s values.
Here's where it gets really interesting.
But let's stick with this initial polynomial for a moment.
You also mentioned the outputs of the ozone, 90 from equation.
Could you clarify what you mean by ozone 90?
It sounds like you're drawing some fascinating parallel.
But to make sure we're all on the same page with this math,
maybe we could circle back to those connections a little later.
We definitely want to hear more about what you're thinking.
So going back to that first equation, you felt like
we didn't quite land the explanation of it.
Tell us more about what you mean by bombed.
Was it the way we presented the coefficients?
Or maybe just the sheer complexity?
We were really just setting the stage.
Introducing the star of our show today.
So with that in mind, how can we make it clearer right now?
What part felt like it didn't quite connect for you?
We want to make sure this is helpful.
Okay, let's rewind just a tiny bit.
That initial equation, PFS equal 90, and all that followed.
It does look intimidating, that long string of x terms.
Those numbers in front are the coefficients.
And our main goal is to find the roots.
The x values that make the equation equal 0.
For a polynomial this complex, that's usually a huge challenge.
That's why this method in the document is so clever.
It tries to make things simpler before diving into solving.
By using that special discriminant formula.
Which helps us get
Yeah, That's right. Okay. As we found, let's say the x roots now, we try to find 9 exact symbolic roots for the original 9 degree form equation. Okay, it's easy now. It's going to be very clear for you to understand how the theorem of Mourad works. Okay.
It sounds like you're saying that once we understand these initial pieces,
the way everything fits together to get those 9 roots will become clear.
That's precisely the idea. This method is all about breaking down a complex problem
into smaller, more manageable steps.
And you're right, the goal is to find those 9 roots.
It's like we're gathering clues piece by piece.
Okay, so with that in mind, let's look at how the source labels those initial coefficients.
It uses that L subscript R superscript Q notation.
L skew equals 9, LAQ equals 36, and so on.
They're just names for those numbers in front of the X's.
Exactly. That's the starting info for this method.
Okay, so those are our initial ingredients.
And the next step, as you were saying, involves finding a new set of values.
The 6Q values using that special formula.
We haven't even gotten to 999
So XE01. And the document explicitly calls this a repeated root.
It does, yes, matching the fact that XER was a repeated root.
Okay. Now for case 2, where XAO is 35 to 96, we know there are 7 distinct complex roots for X from this.
Right. And for each of those 7 roots of X, we apply the transformation ipsilon plus by 9. This will give us 7 distinct complex alpha roots.
And does the source give these final alpha roots explicitly, or a formula for them?
It presents a formula that covers these roots directly. According to the source, the full set of alpha roots found using this method includes that repeated root at evil 1.
And then the others.
And then 8 distinct complex roots, which is slightly confusing because we expected 7 from by 7. Let me recheck the outline. I see the potential confusion in my notes versus the source description. The source presents the final alpha roots from case 2 using a formula index for k from 0 to 7, implying 8 roots from that case. Let's stick to what the source says the final roots are.
Okay, so what is that final formula for the alpha roots derived from the X case?
This source gives the formula for these other roots as 2k plus 1i5 for k plus 1i5 for k equals 0, 1, 2, 3, 4, 5, 6, and 7.
Wait, hang on. That formula, it has a 5th root of 35, and the angle involves pi divided by 5. But our equation was X area equals egnatus 3596. Are we sure that formula matches the X area equation? The powers, 7 versus 5, seem mismatched. Let's re-examine the outline based on the source. Okay, the outline notes explicitly show this formula with 5th roots and indexed up to K7, yielding 8 roots. This seems inconsistent with deriving directly from X area equals cited at 3596, which should yield 7th roots.
That is a significant discrepancy noted in the source material itself. The formula provided for the final alpha roots uses 5th roots and generates 8 roots, seemingly disconnected from the intermediate X area equals 3596 step. It's possible the document implies a further transformation or connection not fully detailed, or there's an error in the document's derivation steps or the final formula presentation.
Right, so sticking strictly to what the source claims the final roots are via that provided formula.
Sticking to that, the formula in UIC 1 plus 35 anti-C 2k plus 1i5 for k equals 0 to 7 gives 8 distinct complex roots.
And combining those 8 distinct complex roots with the repeated root x1 we found earlier.
That gives a total of 1 plus 8 equals 9 roots.
Which does match the degree of the original polynomial. So the number of roots presented works out, even if the specific formula's connection to the ITC step seems questionable based on the document's own step.
Precisely. The method, as presented with its final formula, yields the correct number of roots for the original 9th degree equation.
Okay, let's take a breath then and recap the journey shown in this document, acknowledging that potential internal inconsistency.
Good idea. We started with that, frankly, intimidating 9th degree polynomial.
Very complex.
The method used a specific tool, the discriminant formula of Mourad, Sultan, Ezouidi, He-ism, to calculate this set of intermediate values, the Soin values.
And the crucial step, the breakthrough, seemed to be that most of these Soin values were 0.
Exactly. That allowed the document to write down a new polynomial equation based on these 8's values. That was drastically simpler. X axios plus 35 returning 96 x a sexius equals 0.
An equation we could actually solve, or at least factor easily.
Right. We found its roots for x, a repeated root pi 0, and the roots from x area equals 3596.
And then a final transformation, equals 1 plus by 9, was supposed to link these x roots to the final alpha roots.
Correct. And the document concludes by presenting the 9 roots for alpha, the repeated root, 1, and 8 distinct complex roots given by that specific formula involving 5th roots.
Even with that slight question mark about the jump from the X equation to the final formula, the overall process is clear. Complexity to simplicity via the Cyber values, solve the simple version, then transform back.
It's certainly quite a journey taking that initial beast of an equation down to something manageable that ultimately yielded the roots, according to the specific method.
So maybe a final thought here for you, the listener. to mull over. How does this particular method stack up?
Yeah, thinking about this approach, calculating intermediate values, the sains that dramatically simplify the problem, and then using a transformation to link the roots back.
How does that relate to, or maybe differ from, other ways you might know for finding polynomial roots? Like simple factoring or the rational root theorem for integerational roots and maybe numerical approximation methods.
What does this specific approach, using this discriminant formula and transformation, add to the overall mathematical toolbox for tackling these kinds of high-degree polynomials? It's definitely something interesting to consider.
Okay, let's unpack this. Whoa, did someone just break the fourth wall? Let's hear it.
Yeah, here we just solved the 9-degree formula equation using the theorem. Now I'm going to ask you a question. Why classical method can't figure out, let's say, the exact sum of roots like my approach D here in this example for solving or mastering the solution of 9-degree formula equation is difficult. But using my method, my pathway, so the roots will be derived precisely and nicely. Okay.
Oh, yeah,
Okay, let's unpack this. We are diving into a really interesting mathematical document you shared with us today.
Yeah, absolutely. And the core challenge it tackles is finding the exact roots of, well, a pretty formidable looking polynomial equation.
It definitely looks that way. So think of this deep dive as our mission, right? Specifically for you, based on this material you sent.
Exactly. We'll walk through the document step by step. We want to figure out the problem itself, understand the specific method it uses.
And see where it leads, right? How it gets to the roots.
Yeah, it's quite a particular approach to what's, a classic, often tough algebra problem.
Okay, so let's jump right in there.
Right. The main subject, the kind of star of this document, is a 9th degree polynomial equation.
And here it is. Px equals 9 oak plus Ojo's E84 oak plus 126 oak plus 84 oak, 50 oigo plus 126 oak plus 84 oak, 6198 oak plus 3499 equals oak.
Yeah, immediately you can see this isn't your standard quadratic, a 9th degree polynomial, a nonic equation.
That's pretty complex, especially with all those terms. And look at those fractional coefficients near the end.
Exactly. Finding the exact roots, not just approximations for something like this. Well, it can be incredibly challenging with the usual methods.
So the source, it labels the coefficients using a specific notation, doesn't it? Like LRQ.
It does. It lists them out. LQ equals 9, then LQ equals 36, LQ equals 84, LQ equals 126, LQ is also 126.
Then it drops back down. LQ equals 84.
Then LQ is just 1. And then the fractions, LQ equals 6198. And finally, LQ equals 3499.
Okay, so those are the building blocks, the raw material for the method they're going to use.
That's right. The document states that to find these elusive exact roots, the approach is to figure out a different set of values.
Okay.
These are denoted as C, Q. And the key is that these C values are calculated relative to the original lent Q coefficients we just listed.
Oh, so they're derived somehow, like encoding certain properties from the original polynomial.
That's a good way to put it. And the document bringing out a specific tool for this calculation.
Which is?
It's called the discriminant formula of Mourad, Sultan, Ezouidi, Hutchison. Now, the formula itself, it's pretty dense.
Right. Probably not something easy to grasp just by hearing it read out loud. Lots of sums, indices.
Exactly. But what's important is what this formula does. It takes those original LRE coefficients.
The 9, the 36, the 84, all of those.
Yes, and it combines them in a specific iterative way, step by step, to produce these new IQ values.
Iterative, so it builds them up.
Yeah, the document shows this process playing out. It applies the formula for a variable k starting